Today we are going to discuss about some theory. The first theory for the laboratory manual entitled with Inorganic Pharmacy 2 Lab. We are mainly discussing the theoretical part of the laboratory manuals, and today our discussion will be introduced or inaugurated with the experiment number 1. The name of the experiment number 1 is conversion of different water insoluble or sparingly soluble substances into water soluble form. That means the conversion of different water insoluble solute or slightly soluble solute into water soluble form. And the experiment begins with some introductory terms, and these introductory terms are you are familiar with these introductory terms, particularly during your physical pharmacy 1 lab. We had some discussion on these terms. The terms indicates what is solution, what is solvent, what is solute, what is dissolution, and what is solubility. So let's begin with solution. A solution may be defined as a homogeneous mixture of two or more components that forms a single phase. That means solution is something that will form a single phase and that will produce a homogeneous mixture. For example, whenever you dissolve sugar into water, after complete solution, you will find no sugar, but a sweet solution of sugar and water. This type of mixture is known as homogeneous mixture, and a single phase indicates that sugar is solid, the phase of sugar is solid, the phase of water is liquid, but whenever sugar dissolves into water, ultimately it produces a single phase which is known as a liquid phase. So solution is known as a homogeneous mixture, and it may contain two or more components, and ultimately it will produce a single phase. And another thing, a very important thing, is that solution is the mixture of solution will produce a molecular level of homogeneous phase. That means solution is a homogeneous mixture of two or more components at the molecular level that will produce a single phase. The mixture that is produced after complete solution will be at the molecular level. That means the molecule of sugar has broken down and distributed uniformly in the water, and the water molecule have a bonding with the sugar molecule, and they will produce a uniform homogeneous mixture with a single phase, which will be regarded as a solution of sugar into water. In the similar manner, whenever you dissolve some salt in the water, this will also produce a homogeneous mixture of salt into water, and it will be distributed in the molecular level. The sodium and chloride will be broken down. Sodium will produce sodium plus ion, and chlorine will produce chloride ion, which is a negative ion. This negative ion and positive ion will produce will have some interaction with the water molecule, which have a positively charged hydrogen pole and negatively charged oxygen pole. That is a different thing. We have discussed these things during the physical pharmacy 1 theory class. So today we will not go in that section. Whenever a solution is produced, it will have basically two parts. One part will be regarded as solvent, and another part will be regarded as solute. In the solution, the component that determines the phase of the solution is known as solvent, and it is generally present in larger amount, and it will contain the solute. So the solute is the other part or other component of the solution, which will be distributed throughout the solvent. So solution has two parts. Number 1 is solvent, number 2 is solute. Solvent is the largest portion of the solution that will determine the phase of the solution. For example, in case of sugar and water will be in larger amount, so water is the solvent, and water determines the phase of the solution. That means whenever sugar dissolves into the water, it will produce a sweet solution, and the final phase of the solution is liquid, This liquid phase is due to the presence of water in the solution. Since water is a solvent, it has liquid phase, so ultimately the solution will have liquid phase. And thus in the same example, we have seen that sugar was dissolved into water. So sugar is the solute which is present in a small amount and distributed in the molecular level throughout the water. So according to the definition, sugar will be regarded as solute. I think it is clear to you. Now, the sugar molecule, to produce a solution, the sugar molecule must have to transfer from its solid state into the liquid state. The sugar molecule must transform from its solid state into the liquid state, and this transformation of sugar molecule from solid state into the liquid state is known as dissolution. This is known as dissolution. Another example, we told about the dissolution solution of salt into water. In this case also, the transform of salt molecules from solid state into the liquid state will be regarded as dissolution. So we can say that the transfer of molecules or ions from a solid state into solution is known as dissolution. The dissolution process may be slower, may be faster, and the rate of the solution, rate of the dissolution, that means the rate of the transfer of solid molecule from solid state into the liquid state, will depend upon some experimental conditions or environmental conditions. Whenever the environmental condition is fixed, then the rate of the rate of the transfer of the solute from solid state into the solution will be known as solubility of the solute in the solvent. That means I am saying that for a given set of experimental conditions, the transfer of the solid solute from its solid state into the solution state is known as solubility of the solute in the solvent. For example, in case of sugar candy, white sugar candy, the rate of solution of white sugar candy is very slow. If we left a white sugar candy into a glass of water, it will take an overnight to become dissolved. On the other hand, the rate of solution of sugar molecules is faster than white sugar candy, and the rate of solution of glucose D, for example galactose D or pran glucose D, this type of glucose D dissolves very fast, even more faster than the white sugar cane and the sugar molecules. So we can say that the extent to which the dissolution proceeds under a given set of experimental conditions is referred to as solubility of the solute in the solvent. That means the amount of the solute which can dissolve in a given set of experimental condition will be regarded as the solubility of the solute in the solvent. In this sense, the solubility of glucose D is very high. On the other hand, the solubility of white sugar candy is very low, and the solubility of sugar molecule is intermediate between the glucose D and the white sugar candy. Now let's move on to our next introductory topics. Solution process. How does the solution proceeds on? From the picture you can see that this is the solvent, this is the solute. Whenever the solute in the solid state, it will have its crystal structure. In the picture you can say that it has a definite structure of hexagonal, or and this is the solvent molecule. For example, this is the solvent molecule of water, and you can see that there are some intermediate gaps in the solvent molecule, and the solid molecule have no intermediate gaps. It has a definite pattern. Whenever a solute is dissolved or placed in the solvent molecule, then the solute molecule breaks its bond and the individual molecules moves apart. If it is sodium chloride, then this might be sodium, this might be chloride, this might be sodium, this might be chloride. They moves apart and it will take some energy. And on the other hand, to consume that solute molecule, the soluble molecule also rearranges its shape. For example, this may be water and this may be hydrogen part, this may be oxygen part, this may be hydrogen part, this may be oxygen part. They have weak interaction with them. Now ultimately the negative and positive pole of water will have interaction with the negative and positive pole of sodium and chloride, and the solid molecule will fit inside the gap between the solvent molecules. In this way the solution proceeds. So we can say that in order to dissolve a solid, the particles of solvent must be able to separate the particles of solute and occupy the intervening space. That means to dissolve a solid, this is a solvent molecule. If this solvent molecule wants to dissolve a solid, it must be able to separate. That means it must be able to create some gap inside them, and this gap will be occupied by the solid molecule, and ultimately they will produce a solution. This happens when the positive end of the solvent molecule approaches to the negative end of the solid molecule. I already told you that if it is water molecule, then water molecule will have a positive pole of hydrogen ions and a negative pole which will be created with or composed of oxygen molecules. This will happen because there is a difference in the electronegativity between the hydrogen molecule and the oxygen molecule. Oxygen is more electronegative than the hydrogen molecule. That is why they will produce a bipole, or the molecules will have a different poles or different charges. One is positive charge, another is negative charge. On the other hand, in case of sodium chloride, whenever sodium chloride is placed in water, sodium will be separated from the chloride molecules, and sodium will have plus ion known as sodium ion, and chlorine will have negative charges known as chloride ion. This chloride ion will interact with the positive poles of hydrogen ion present in the water molecule, and the positive sodium plus ion will interact with the negative pole of water molecules known as oxygen ion, and in this way they will form a bond between them, and the sodium chloride molecules get dissolved inside the water molecules. As we are saying that the solid molecule is pulled into the solution when the force between the solvent solute molecule overcomes the attractive force between the solute molecules themselves. Therefore, the solute will be soluble in the solvent if the solute-solvent attraction is stronger than the solvent-solvent attraction and solute-solute attraction. That means the solute molecule will have attraction between them. One solid molecule will attract another solid molecule. In the similar manner, one solvent molecule will attract another solvent molecule. During the solution process, the attraction between two solvent molecules or the attraction between two solid molecules must be weaker than the attraction between solid molecules and solvent molecules. The attraction between solid molecules and solvent molecules. Whenever the attraction between solid molecules and solvent molecules is stronger, then the solid molecule will have interaction with the solvent molecule. Conversely, we can say that the solvent molecule will have interaction with the solid molecule, and in this way they will form a solution. So the attraction between two solid molecules must be weaker. On the other hand, the attraction between two solvent molecules also must be weaker, but the attraction between the solid molecule and solvent molecule, solid molecule and solvent molecule must be stronger. In this way, solution process takes place. If we want to know a particular example of solution, you can take the book written by Ball Tuli known as Essentials of Physical Chemistry, and you will have an example of the solution process. Example was given for the solution process of sugar in the water. Okay, and ionic solid dissolves in water because the number of water molecules around the surface is greater than the number of other ions of the solid. The attraction between polar water molecule and a charged ion enable the water molecule to pull ions away from the crystal, a process called dissolving. It implies that whenever whenever an ionic solid, for example sodium chloride, is placed in the water, the sodium chloride will have interaction with the water molecule, and what will happen, the positive pole of sodium, positive pole, that means sodium plus, will be attracted by the negative pole of the water molecule, which is created by oxygen. That is why the sodium will leave the chlorine. The interaction between sodium and chloride will be weaker, and the interaction between sodium plus and the oxygen of the water will be stronger. That is why sodium will leave the chlorine and will form a bond with the oxygen molecule of the water. In the similar manner, the attraction between the chlorine and sodium will also become weaker, and the chloride ion will leave the sodium and will form a bond with the hydrogen part of the water. In this way, sodium chloride gets dissolved in the water, and that has been told in this part of the manual. So generally we know that the polar substances, for example methanol, can be easily dissolved in water. Polar substances like sodium chloride can be easily dissolved into water, but non-polar substances, for example oil, any kinds of oil, mustard oil, coconut oil, is not will not dissolve in the water. This is because polar substances can be dissolved only in the polar solvent, and non-polar substances can be dissolved in the non-polar solvents. That is why benzene, naphthalene, and that can be dissolved in carbon tetrachloride, but not the polar substances like sodium chloride. This rule is known as like dissolves like. Like dissolves like. There are some factors which affect the solubility of solute. You know that these factors are you have already taught that the 5 factors that can affect the solubility of solute during your physical pharmacy 1 class. The factors were: number 1, temperature. You know that temperature can affect the solubility of solute. In case of endothermic process means the process that absorbs temperature. The solubility increases with the increase in temperature and vice versa. In case of endothermic process, the endothermic process is the process where temperature decreases or that absorbs temperature. For endothermic process, the solubility increases when the temperature is increased, or inversely, when the temperature is decreased, the solubility will be lower in case of endothermic process. For example, the solubility of potassium nitrate increases with the increase in temperature. Since the whenever potassium nitrate is dissolved, it produces a lowering of temperature since it is an endothermic process. So to increase the solubility of potassium nitrate, we have to increase the temperature. If we increase the temperature, the solubility of potassium nitrate will be increased. On the other hand, in case of exothermic processes are those processes where the temperature increases. The process that produces temperature is known as exothermic process. In case of exothermic process, the solubility decreases with the increase in the temperature. That means in case of exothermic process, if we increase the temperature, the solubility decreases. On the other hand, if we decrease the temperature, the solubility increases. For example, the solubility of calcium oxide decreases with the increase in temperature. You know that whenever calcium oxide is dissolved in water, it produces lots of heat since it is an exothermic process. So if we increase the temperature is already increased, and if we increase the temperature, it will decrease the solubility of calcium oxide. And this is true because you know that according to the Le Chatelier's principle, this process or any chemical reaction will do anything to minimize or reduce the effect of change whenever it is in the chemical equilibrium. This is the principle for their decreasing of solubility. Anyway, the main thing is that in case of endothermic process, temperature increasing the temperature will increase the solubility. In case of exothermic process, increasing temperature will decrease the solubility, and this is vice versa. Number two, effect of pressure. Effect of pressure is applicable only for gases. You know that whenever the temperature pressure is increased, the solubility of gas also increases, and this principle has been applied for making the soft drinks, for example 7-Up, Coca-Cola, etc. The carbon dioxide gas is dissolved inside the soft drinks, and the solubility of carbon dioxide increases whenever the pressure is increased. That is why after opening the bottle cap, the pressure decreases, and the carbon dioxide which was previously dissolved inside these soft drinks becomes comes out from these soft drinks in the form of bubbles. I think it is clear to you that pressure increases the solubility of gas. Okay, number three, chemical nature of the solute and solvent. I already discussed with you that polar solvents, for example water, can dissolve polar solute, for example sodium chloride, but polar solvent water cannot solubilize or dissolve non-polar solvent like oils. Any kinds of oil is insoluble in water because oil is non-polar and water is polar. So polar solvent can only solubilize polar solute. On the other hand, non-polar solvent can only solubilize non-polar solute. This term is known as solute like dissolves like. And so the chemical nature of the solute and solvent is very important for making a good solution. If you are trying to make a solution of oil in water, it will not be a wise choice because oil is nonpolar and water is polar. So the chemical nature of oil and water are different and they will not produce a solution, and that is another factor that will affect the solubility of solid in solvent. Number four, stirring. With liquid and solid solute, stirring brings fresh portion of the solvent in contact with the solute, thereby increasing the rate of dissolution. Whenever you are trying to make a solution and you are not stirring the solvent, then the rate of production of the solution will be very slow. But if you use a stirrer and produce a gentle stirring, then it will produce more faster solution than ever before. This is because whenever you stir the solvent, the part of the solvent which do not contains any solute will come in contact with the solute. That means fresh solvent will come in contact with the solute, and the solute can easily become dissolved within the fresh solvent. In this way, the amount of solute dissolving in the solution increases. But if you do not start the solvent, the solute will be dissolved in the solvent at a very small rate, a slow rate, because after some time, at the beginning the solute will be dissolving in the solvent, and after some time the solute will have a saturated layer around itself, surrounding itself. It will have a layer of solvent which is saturated with the solute surrounding itself. So the rate of solute dissolving in the solution will be lower. But if you start the solution, the solute will have a new layer of solvent that have no solute. That is why the solute can be easily dissolved in the solvent and will become dissolved and produce the solution at a faster rate. Number 5, amount of solute already dissolved. This is another important factor, the amount of solvent already dissolved. If the amount of solvent already dissolved reaches the saturation point of the solution, then it will not allow you to dissolve any further amount of solute, because you know that there are three types of solution: unsaturated, saturated, and supersaturated. Unsaturated solution means the solvent has is not quenched with the amount of solute that it can take. That means it has a larger capacity to dissolve the solute, and the amount of solute you have dissolved is not enough. So this is not a dilute solution or unsaturated solution. A saturated solution is the solution which has the exact amount of solute that it can take or it can dissolve. And supersaturated solution is the solution where it contains more than the saturated concentration of the solution. That is why the if you have chosen a solution which is already saturated with the solute, then you will not be able to dissolve any amount of solute. So you have to take a fresh solute, fresh solvent, and or otherwise you have to take a dilute solution so that you can dissolve the solution. So when there is a little solute already in the solution, dissolving takes place relatively rapidly. That means when you have taken a fresh solvent or dilute solution, then you can dissolve the solute at a rapid rate. On the other hand, if you take a saturated solution or saturated solvent or supersaturated solution or supersaturated solvent, then you will not be able to solubilize any amount of solute. As the solution approaches the point where no solute can be dissolved, dissolving takes place more slowly. Number 6, molecular size. The larger the molecular size of the solute are, the larger is their molecular weight and their size. If the pressure and temperature are the same, then out of two solutes of same polarity, one with smaller particles is usually more soluble. This implies that whenever you have taken a large sized solute, for example, white sugar candy, white sugar candy is large in amount. On the other hand, and you have taken glucose D, the size of the glucose D is very small. This is like just like a fine powder. So the molecular size of glucose D is very small. It is just like a fine powder. On the other hand, the molecular size of white sugar candy is large. It has heavy weight. Among these two things, the white sugar candy will have low solubility rate. On the other hand, the fine powder of glucose D will have larger solubility rate, and this is because of the molecular size. So if you want to produce the solution at a faster rate and uniform solution, you have to choose the solute which is in the powder form or which have at least a small molecular size. Now, why the solubility is important in pharmacy? Solubility is very important in pharmacy. You know that whenever we take any kinds of drug orally, after taking the drug in the oral form, for example, if you take Napa Extra or Napa or another form of paracetamol tablet in the tablet form, after taking the drug, it will go into the stomach. Then it will produce a solution in the stomach, and after producing solution, it will enter into the blood stream, and then the blood will carry the drug at their site of action. If you have headache, the blood will carry the drug to your head, and if you have toothache or if you have muscle ache, then the blood will carry the drug into the tooth, or the blood will carry the drug into your muscle. So for any oral drug to be effective, any kinds of oral drug to be effective, it must be dissolved into the stomach. At the same time, it must be transported to the blood. So solubility is very important for oral solid drugs. But so we can say that solubility is one of the important parameters to achieve desired concentration of drug in the systemic circulation for asemic required pharmacological response. I have already told you that to get the pharmacological response or your desired response, the drug must be conducted to the site of action by the circulating blood system known as systemic circulation. Poorly water-soluble drugs often require high dose in order to reach the therapeutic plasma concentration after oral administration. This implies that whenever the drug has poor solubility, if the drug does not dissolve enough, then you have to increase the amount of drug you have taken. If you have taken a tablet which contains 500 milligram of the drug and it is not completely soluble, then you have to take more drug. 500 milligram, maybe it is 10% soluble. That means 500 milligram drug, you have taken 500 milligram drug, but if it is 10% soluble, that only 50 milligram drug will be dissolved into the stomach. Then to get your desired action or pharmacological action, then you have to take more drugs. That has been told in this line, that you have to take high dose or more drugs to get your therapeutic action. Most of the drugs are either weakly acidic or weakly basic, having both aqueous solubility. You know that most of the drugs, for example paracetamol, it is weakly acidic. Paracetamol is a para amino acetaminophen. Paracetamol, known as NAPA, N-acetyl para-acetaminophen. This is a weakly acidic drug. It has low or poor water solubility, but it must be soluble in the stomach, and the soluble and the stomach contains water, so it will be soluble in the water. These poorly water soluble drugs having low drug absorption leads to inadequate and variable bioavailability and gastrointestinal mucosal toxicity. If the drug is poorly soluble or very small soluble or sparingly soluble, then it will be dissolved in small amount into the stomach, and the amount of drug that reaches the systemic circulation will be also will be small in amount, and that will not produce the desired plasma concentration. And if the plasma concentration is not in the at the desired level, then the therapeutic action will be below the desired level, or there will be no therapeutic action. On the other hand, if we want to get more drugs to be dissolved into the to be present into the blood circulation, then we would require a high doses of the drug. And if the dose of the drug increases, then the amount of the drug present in the stomach will be greater. And if the amount of the drug present in the gastrointestinal mucosa is greater, then there will be a toxicity known as gastrointestinal mucosal toxicity. For orally administered drugs, solubility is the most important one rate limiting parameter to achieve their desired concentration in the systemic circulation to get pharmacological response. I have already told you that what does it implies. Solubility also plays a major role for the dosage forms like parenteral formulations as well. Parenteral formulations are those formulations which generally administered through injection. There are different types of injection: intravenous, intra-arterial, intrathecal, etc. etc. Whenever any drug is administered through injection is known as parenteral drugs. And in case of parenteral drugs, the solubility also important parameter. But for orally administered drugs, for example naproxen or any other tablets or capsules, solubility is the most important, because if the drug is not soluble, it will not produce it will not get transported into the blood, because for a drug to be effective it must be transported into the systemic circulation or into the blood circulation. So to get into the blood circulation, the drug must be solubilized into the stomach, and that then it gets into the blood, and the blood will take the drug at the site of action, and we will get our desired pharmacological action. So solubility is the rate limiting step for any oral solid dosage form for any oral solid dosage form to get the desired pharmacological action. If it is not enough soluble, then we will not get our desired pharmacological action. That's all. Here is a chart method for expressing concentration. You know that what is mole fraction. Mole fraction is the ratio of mole of one constituent to of a solution to the total moles of the constituents. That means the moles of solute and solvent. What is mole percent? Whenever the mole fraction is multiplied with 100, it is known as mole fraction. Percent by weight means mole masses of solute divided by total mass of solution into 100. Percent by volume, it is known as volume of solute divided by volume of solution into 100. Percent by weight in volume, it is known as mass of solute divided by volume of solution into 100. And percent by volume in weight, it means volume of solute divided by weight of solute into 100. Basically, we deal with these three parameters: W by W, W by V, and V by V. There is also parts by mass, which is known as mass of solute divided by mass of solvent into multiplication factor. If the multiplication factor is 10 to the power 6, this is known as parts per million. And if the multiplication factor is 10 to the power 9, this is known as parts per billion. Now let's move to our principle. The principle states that solubility is the phenomenon of dissolution of solute in solvent to give a homogeneous system is one of the important parameters to achieve desired concentration of drug in the systemic circulation to get the anticipated pharmacological response. This slide implies that solubility is very important phenomenon. Solubility, what is solubility? Solubility is the rate and extent to which a solute gets dissolved under a given set of experimental conditions. That means whenever a solid gets dissolved into a solution, that it becomes liquid, and the rate of this solution, that means the rate in which the solid particles becomes a part of solution, solid becomes liquid, the rate of the dissolution is known as solubility. And dissolution and the solubility is very important because if the drug is not soluble enough, then it will not produce a desired concentration in the systemic circulation or at the blood. And if the concentration of the drug in the blood is not enough, then it will not produce the desired pharmacological response. For example, you have got fever, you have taken Napa extra. The Napa extra didn't dissolve in your stomach. So if Napa extra do not dissolves in your stomach, the paracetamol will not reach into the blood. If the paracetamol do not enters into your blood, your fever will not become lowered, or you will not get rid of your fever. So to get rid of your fever or become a healthy person from a fever, if you are suffering from fever and if you want to get rid of this fever and become a healthy person, you have to take oral drug, and the drug may be Napa extra, etc. You have taken Napa extra and the Napa extra didn't dissolve at your stomach, and if the Napa extra do not dissolve in your stomach, you will not get any drug in your systemic circulation or in your blood. If there is no drug in your blood, then you will not get rid of your fever, and there is nothing to do with that drug. So for the drug to be effective or the drug to be active, it must be dissolved into the systemic circulation, and to dissolve into the systemic circulation, it have to dissolve into the stomach. That's all. Low aqueous solubility is the major problem encountered with formulation development of new chemical entities as well as for the generic development. Generally, the drug we take, for example, paracetamol or ciprofloxacin, whatever the drug is, generally it has low aqueous solubility. That means the solubility of this drug in the water is very low, and it is a major problem. More than 40% new chemical entities developed in the pharmaceutical industry are practically insoluble in water. It implies that about 40% of new chemical entities, that means new drug that is going to be developed, is generally insoluble in water. This is very big problem. About 50% of the chemical, 40% indicates about 50% of the chemical is insoluble in the water. But we need water soluble drugs. So any drug to be absorbed must be present in the form of solution at the site of absorption. We already told you that 40% of the chemicals is insoluble in the water, but if we want to get any response or any pharmacological response from the drug must be solubilized into the water. If the drug did not solubilize into the water, it will not be able to enter into the systemic circulation or into the blood. And if it do not enters into the blood, then it will not be able to reach the site of action. These lines are repeating. I am repeating these lines for several times. I already repeated several times and repeating continuously. Various techniques are used for the enhancement of solubility of poorly soluble drugs, which include physical and chemical modification of the drug, and other methods like particle size reduction, crystal engineering, salt formation, salt dispersion, use of surfactant, complexation, and so forth. So it is clear that solubility is a major concern for orally administered drugs. And if the drug is not soluble, and already told that 40% new drugs are not soluble in the water, so to increase the solubility of the drug in the water, various techniques are used. The technique includes particle size reduction. And we have discussed that if the particle size is large, then it will have low solubility rate. If the particle size becomes smaller, then it will have a higher solubility rate. And the example was glucose D. Glucose D becomes solubilized at a faster rate than white sugar candy. Next, second one is crystal engineering. This is crystal form is generally more soluble than the general form. That is why sodium chloride is very soluble. Salt formation, you know that salt formation also produces a soluble at any salt. Generally, any salt is very much soluble in the water. It is a sodium chloride, potassium chloride, etc. etc. These types of salt are very soluble in water. Solid dispersion. Solid dispersion indicates that the drug should be if the drug is semi-solid, then it would be converted into solid, and the solid generally disperse well in the water, since we can stir the solid into the solvent. Use of surfactants. Generally it is this surfactant is applied for the production of emulsion. Emulsion makes insoluble water and oil solubilized, and these surfactants can increase the solubility rate of oil into the water. Complexation. Complexation is another term which is used for the increasement of the solubility of solute into the solution. Complexation is proceeds by making a complex form. For example, there is a complex form is formed between the solute and the solvent, and so other forms. Selection of solubility improving method depends on drug property, site of action, and required dosage form characteristics. This implies that which method we will use. For example, whether we should use particle size reduction or salt formation depends upon the property of the drug, the type of drug we are using, where the drug to be absorbed, whether it is orally administered or it would be applied on the uh, upper surface of our body, or topical applied, or it would be just like a gel or cream or ointment, whatever the form of the drug. Then according to that, there will be the method for increasing the solubility of the drug and the required dosage form characteristics. So this is the principle of our labs, and there is a chart that defines the solubility. Very soluble, a part of solvent required to dissolve one part of solute. Very soluble indicates the one part, less than one part of solvent is required to dissolve one part of solute. For example, if we take 1 gram of sugar and if we take 1 gram of liquid water, then liquid, if 1 gram of liquid water is enough to dissolve 1 gram of sugar, then we will say that sugar is very soluble, freely soluble, that requires 1 to 10 parts of solvent. For example, if we take 1 gram of sugar and if this 1 gram of sugar can be dissolved with 1 to 10 gram of water, then we will say that this sugar is freely soluble. 1 gram of sugar and 1 to 10 gram of solvent, that is 1 to 10 gram of water. Soluble. What is soluble? If we take 1 gram of solute and the solute can be dissolved with 1 gram to 30 gram of solvent. 1 gram of solute can be dissolved with 10 to 30 gram of solvent, then we will say that this solute is soluble. For example, if we take 1 gram of salt, just like sodium chloride, 1 gram of sodium, if 1 gram of sodium chloride can be dissolved with 10 to 30 gram of water, then we will say that sodium chloride is soluble. Sparingly soluble. What is sparingly soluble? If we can solubilize 1 gram of solute with 30 to 100 gram of solvent, then we will say that it is sparingly soluble. For example, uh, benzoic acid. Benzoic acid may not be soluble with 1 gram. 1 gram benzoic acid may require more than 30 gram of solvent. That is why we will say that it is a sparingly soluble solvent. Slightly soluble. What is slightly soluble? When 1 gram of solute requires more than 100 up to 1000 gram of solvent, then we will say that it is slightly soluble, very slightly soluble. When you need 1 gram of solute and you have to dissolve this solute, but you are not able to dissolve this solute unless you use 1000 to 10,000 gram of solvent, then we will say that this is very slightly soluble. And practically insoluble, after you have taken 1 gram of solute and you are applying solvent and you are applying solvent and the solvent have overcome 10,000 gram. After 10,000 gram, your solute is still not soluble, is still insoluble, so we will call your solute as practically insoluble. For example, if you take a little bit of wood, of any kinds of wood, if you take little bit of wood, little bit of brick, little bit of soil, the soil is insoluble in water, wood is insoluble in water, brick is insoluble in water, plastic is insoluble in water, and if you take more than 10,000 part, the plastic, the wood, everything, the iron, they will not become solubilized. That is why they are practically insoluble. So what we are going to do, we are going to solubilize some practically sparingly soluble substance, and our solid sample reagent indicates we have salicylic acid and benzoic acid. In general, salicylic acid, 1 gram of salicylic acid requires 460 ml of water. 460, this m is extra. 1 gram of salicylic acid will require 460 ml of water. If we consider that 1 ml of water is equal to 1 gram of water, then we can say that 1 gram salicylic acid requires 460 gram water. That means 1 part requires 460 part solvent. And according to our chart, if anything that requires the solvent which is between 100 to 1000 part, then it will be regarded as slightly soluble. It will be regarded as slightly soluble. Since salicylic acid requires 460 ml, or we are saying that 460 gram solvent, then we can say that 1 part of solute requires 460 part solvent. That is why it is slightly soluble. Slightly soluble. So if we administer salicylic acid in this pure form, it will not be solubilized in the stomach. Salicylic acid will reduce our pain, but if we place the salicylic acid in its pure form, it will require 1 gram salicylic acid will require 460 ml water, but our stomach do not contain as much water, so salicylic acid will not be solubilized, or the solubility, so the solubility of the salicylic acid should be increased, so the salicylic acid so that the salicylic acid can become solubilized within a very short period of time and can get reached into our blood circulation. And for this thing we have to make a salt of salicylic acid. So in practice, in the practical session, we will uh, react the salicylic acid with sodium carbonate. So salicylic acid and sodium carbonate will produce a salt of salicylic acid known as sodium salicylate, and we know that salt form generally gets dissolved very quickly than its general form, so it will require less amount of water and it will become solubilized within a short period of time. So as our title indicating that we are going to convert, we have to convert some sparingly or insoluble substance into water soluble form, and we will take salicylic acid, which is practically slightly insoluble in water, but when we react the salicylic acid with sodium carbonate, it will produce a salt, and the salt of salicylic acid known as sodium salicylate will become solubilized within very short period of time. That means its solubility will increase. Whenever the practical session runs, you will see that how the solubility of the salicylic acid becomes increased. So, and we have got another drug known as benzoic acid. This benzoic acid is also slightly soluble or sparingly soluble, slightly soluble, because 1 gram of benzoic acid requires 300 ml of water. If 300 ml of water is equal to the 300 gram of water, then we can say that 1 gram or 1 part solute requires 300 part of solvent. And according to the chart, if 1 part of solute requires 300 part of solvent, then it is known as slightly soluble. This is known as slightly soluble. Whenever 1 part of solvent or 1 part of solute requires the amount of solvent which is between 1000 to 10,000 part, 300 is between 100 to 1000 part, so 1 part of solute requires 300 part solvent, so it will be regarded as slightly soluble. So if we administer benzoic acid, which is also a painkiller type of drug, then it will require 300 ml of water. 1 gram benzoic acid will require 300 ml of water to become dissolved, and it is very time consuming, and the amount of water is not present in the stomach, so the amount of drug enters into the systemic circulation will be very low. That is why we have to increase the solubility of benzoic acid, and to do so we are going to react benzoic acid with sodium hydroxide. Whenever we react benzoic acid with sodium hydroxide, it will produce sodium benzoate. This sodium benzoate is a salt and it is very soluble in water, and this sodium benzoate is very soluble in water. That is why it will require a less amount of water, also less amount of time to become dissolved, and will produce its pharmacological action or dissolved action within very short period of time. So this will be our practical. We will take these two types of drugs, salicylic acid and benzoic acid, and we will modify the salicylic acid and benzoic acid. At first we will try to solubilize benzoic acid and salicylic acid in its pure form. Afterwards, we will convert the salicylic acid, also the benzoic acid, into its salt form. Then we will observe how its solubility pattern changes. And that's all about today's practical. Thanks to all for participating in this class.